Chris, the science community, those who have a vague interest in the cosmos, are ordinary plebs like me, fascinated by the James Webb Telescope images that were released this week. In terms of an absolute lay person, why should we be as excited as the scientists and the cosmologists and the astronomers are this week? I saw some of the live footage coming from, I think it was like a NASA office, and you could see some of the scientists. Either there was no clapping, there was no cheering, it was all just wow. Must be amazing to be in that field at the moment, isn't it?
Well, when you've spent 3 billion on something, you need to know it's going to work, and so they had a once in a lifetime chance to make sure it didn't go wrong. They had to perform. So I think a lot of that is kind of people's blood pressure dropping as they go, oh, thank goodness for that. It's okay. But this is the most powerful telescope that's ever been built, and it's doing what Hubble did on steroids. The Hubble Space Telescope was a revolution in astronomy and space science because it was a space telescope. Now, why am I labouring this point? Because hitherto we had been doing our observations of the cosmos from the Earth's surface, and that meant between us and the thing we wanted to look at, there was this problem of the Earth's atmosphere. We've got to see through the atmosphere, and if you look at the night sky and see stars twinkling, you can immediately see the problem, which is that because of the atmosphere and the aberrations and the twisting and bending that it applies to the light coming to us, things in the night sky wobble around, so you get blurry images, and that's why stars twinkle. So, if you put your telescope out beyond the reaches of the atmosphere, you get beyond that problem. And that's what Hubble did. And Hubble really took us to the next level. And so scientists then began to dream up what they were going to do next, because there are things that Hubble can do, but there are things it can't do. There are questions it can't answer. And with, in that movie Jaws, where I think Robert Shaw is told by Chief Brody's character, you need a bigger boat. Well, it was obvious that we needed a bigger telescope, because the bigger the mirror, the bigger the collecting area, the more light we can collect, the dimmer the signals we can see, and therefore the farther we can see. And with the James Webb, what they're doing is looking almost to the edge of the universe that can be seen. And that means we're seeing back almost to the beginning of time. Because if we assume time starts to tick with the Big Bang about 13.8 billion years ago, if you have a telescope that's seeing in the infrared, which this is, it's parked out in space at a Lagrange point, which is a gravitationally stable place in the solar system. It's very cold there, which means it doesn't get disturbed by heat signatures coming from things it shouldn't be near or shouldn't be disturbed by. And it's looking in the infrared, so heat, and those wavelengths can come straight through clouds of gas and dust that would block or scatter visible light. So we get the clearest, purest images in a new regime of the spectrum of far distant objects. We'll even be able to see through the atmospheres of distant planets and work out what's in them. Because as the planet goes in front of its parent star, you will notice the light changing a bit, corresponding to the chemical makeup of the atmosphere of that planet. The Webb telescope will pick that up, and we will therefore be able to see what's in the air around distant planets, which to my mind boggles my mind.
We have a few messages and questions on the James Webb Telescope images in our WhatsApp line, but let's go to the phone lines first. I think it was Paul. You called in first. Good morning, Paul.
Good morning to you, and thanks for taking my call. My question to Chris is, what effect would the adrenal gland have on a human body if it excretes more than it should be?
Hello, Paul.
Thanks so much for that, Paul.
The adrenal glands are called the adrenal glands because they sit above your kidney on each side, and they're this sort of wedge-shaped piece of tissue which is multi-layered. And there's an outer layer called the cortex and an inner layer called the medulla. And they do different things. The medulla in the middle is a yellow colour, and it contains cells called chromaffin cells, and they are yellow because they churn out adrenaline and its chemical relative noradrenaline. And so when we want to get excited about things and we want a big surge in adrenaline, you literally do get that because the sympathetic nervous system says to the adrenal medulla, churn out adrenaline, and it goes around your bloodstream, and it has effects on all of your tissues in your body, boosting metabolism, widening your pupils, making your heart race, putting up your blood pressure in certain parts of the system, and making you breathe faster and opening up your airways. If you get a tumour there, you can get abnormal production of adrenaline, and then you have things like anxiety attacks or panic attacks or bouts of extreme high blood pressure, and that is called a pheochromocytoma. But what you're referring to is a different kind of growth that can happen on the adrenal gland, which is in the outer layer, the rind of the adrenal gland, which is called the adrenal cortex. And that site of the adrenal gland makes a different kind of chemical signal. It produces the hormone cortisol. And cortisol is absolutely critical for life. It keeps us healthy, keeps us happy, gets us out of bed in the morning, literally, because when you have signals coming from your brain's pituitary gland, including one called ACTH, it activates cells in the cortex, and those cells then churn out cortisol. That cortisol goes around your body, visiting every cell and changing the pattern of genes that are turned on or off in those cells, and thereby controlling your metabolism, controlling the level of glucose in the bloodstream, controlling the amount of sodium in the body, and therefore basically controlling how well you are. And if you develop a tumour there, and it doesn't have to be a cancerous tumour, it can be a benign growth there, sometimes that tumour growth can become autonomous in its production of cortisol. In other words, it doesn't need the signal from the brain anymore, which is keeping the level correct. It just starts churning the stuff out. And when that happens, you start to make too much cortisol, and you develop a condition called hypercortisolemia, and that makes people look like they're on steroids, and they tend to have they get quite bloated in the face. You can redistribute fat around your body, you get high blood pressure, and people can become diabetic. And under those circumstances, it can sometimes be treated with drugs that block the production of the cortisol, or they can find where it's coming from and remove the affected adrenal gland or part of the tissue, and it usually can stop the problem.
Paul, really appreciate it. Andre, good morning. How are you?
Good, thanks. Good morning, Lester and Dr. Chris.
Go ahead.
My question is this. If there are about 7 billion people on the planet now, how many people have ever lived?
It's a fascinating question. Chris?
Well, the answer is, in fact, there's probably more like 8 billion people on Earth right now. But we can calculate how many have ever lived. I don't know the number immediately in my mind, but we did this as a question a few years back, because there is this age-old claim that there are more people alive now than have ever lived. It's absolute rubbish. The number of people who've ever lived is in the hundreds of billions, because if there are 8 billion around now and they've all got two parents, etc., you can work it backwards, and they're well north of 100, 200 billion people. So it's a lot of people, but I don't know the precise number.
Let's go to another question. Yeah, Andre, I hope that answers your question in the hundreds of billions. Hi, Dr. Smith. Some time ago, I read an article where the CEO of Levi's Jeans says he doesn't wash his jeans, but puts it in the freezer to clean it. I've also heard this, and I have also know people who very seldomly wash their very expensive jeans. But can this work? Does freezing kill germs, and how do you get rid of stains? Asks Warren.
Hello, Warren. It will work in some respects, but not in other respects. You're quite right. If you've got stains, what's a stain? Well, a stain is a coloured chemical which is latching onto the fabric of a material and therefore changing its colour properties. And just cooling it down won't necessarily divorce that material from the fabric. Therefore, it won't get rid of stains. If you've got oily stains, for example, or other muck on there, putting it in the fridge, putting it in the oven, it's not going to make any difference. You need to dissolve those stains out by using some kind of washing detergent that will remove them. The way most detergents work, and most detergents these days are what we call biological detergents, they contain enzymes, just like your digestive enzymes, which at low temperature washes will get into the fabric, and then they start to, like a pair of molecular knives and forks or scissors, chop up the molecules that cause stains and detach them by breaking the association between them and the fabric to clean your clothes. That is not going to happen in a fridge. So if your clothes are relatively clean, but they've just got muck on them from you, as in some bits of hair and a few flakes of skin and so on, perhaps putting them in the fridge would kill off, or in the freezer would kill off any bacteria, or some bacteria, not all, but some, and that would help to reduce the bacterial burden of your clothing, and some of the stuff would fall off. But I think, to be quite honest with you, if you want something to be clean, you're going to have to put it in the wash, liberate some of the water-soluble muck away, and use some washing powder to liberate the stuff that's sticking to the fabric chemically, to get rid of that and make the clothes look nice as well.
When I get to some James Webb Telescope questions, here's another one that asks, what are we expecting to see when we actually get to see the beginning of the universe with regards to James Webb Telescope? Could we technically see the moments? And we know that the images that we are seeing now is from essentially 13 billion years ago. That's how long the light has taken to travel for the James Webb Telescope to see. Could we theoretically see to the moments just after the Big Bang, Chris?
When the universe first began with the Big Bang, which we think was about 13.8 billion years ago, it was an infinitesimally small part of space with a huge release of energy. And just as Einstein told us, E equals mc squared, energy and mass are interchangeable. So this outpouring of energy that was the Big Bang was subsequently converted from energy into mass, stuff, matter. And that matter began to blow up like a balloon. It was very, very hot, and it inflated very, very quickly. And at some point subsequent to that, things cooled down enough, because as things expand, they get cooler. That's one of the rules of physics. And at one point, things will have got cool enough that things could then coalesce together to form physical atoms. And most of it would have been hydrogen, a bit of helium, and a trace of lithium, the first three elements in the periodic table. And they would have then begun to coalesce together to form clouds of these atoms, which would then, under the effect of gravity, form the first stars. And those first stars would have been massive, burned very, very hot, very, very bright, produce enormous amounts of radiation. And in that way, they would have lived for a short time, blasted themselves to pieces, and produced more elements and more parts of the periodic table, and then spawned that process to keep on repeating as the universe grew and aged. And at certain points after the Big Bang, we then get to a point where space is sufficiently clear, we can see through it, we can see what those star configurations were, where they were, where the gas and dust was. If we can see back that far by looking at distant objects, because the universe is still growing, and so if we look at distant objects, they're going away from us because the universe is getting bigger all the time, and the farther away we look, the farther back in time we look, because light takes time to reach us. This gives us an insight into what the composition of the early universe actually was, what the numbers of different, or representations of these different stars was, where they were, and this can inform the models that physicists run in computers to try to build simulations of that process I just described, how we think the universe began to assemble itself, build itself, and evolve to reach what we are at today. And so by looking back in history, we do almost cosmic archaeology, where we can see back far enough in time to constrain the structure and the parameters in our simulations to get more accurate simulations, and then work out whether we can get a simulation that really does arrive, if you wind the clock back to the beginning, at what we see today. And then we know we're getting close to understanding how the universe is evolving and how it's built itself. And then we can begin to probe questions like where the dark matter is, and how dark energy, which is driving the expansion of the universe, how those figure and contribute to the equation.
Good morning, Lester. Why does drinking water stop a cramp straight away? Asked this listener, Chris.
Well, I don't think it necessarily will stop it straight away, because I've had cramp in the swimming pool and it nearly made me drown, and I swallowed an armload of water and it didn't make it go away. The answer is cramp is a spasm in your muscle, and it's probably a group of muscle fibres which autonomously fire off more than they should do, stop obeying the signals from the nervous system, and just go into this prolonged contraction, which is applying more stress to the surrounding structures than the muscle should do, and that's why it's uncomfortable both for the muscle and the surrounding structures. It can happen for a range of reasons. One reason is because of electrolyte imbalance. Muscles are electrical organs, and they arrive at that electrical excitability because they pump sodium and potassium out of and into cells, respectively, and they use calcium to trigger the muscle to contract. So if there is a problem with your electrolyte balance, the dissolved salts in your body, then it will make your muscles more or less electrically excitable and more or less electrically unstable. And this can be a risk factor. And so, therefore, if you are dehydrated, you've lost a lot of salt, you are at higher risk of this happening. And so it may well be under certain circumstances that if you put that water back in, then you help to reset the equilibrium, and that will help your muscles to be more in balance and operate more the way they should.
Let's go to the phone lines now. Temba in Lansdowne. Good morning, Temba.
Good morning, Lester. My question is, today Chris was speaking about time as if it's an objective phenomenon. And maybe 2 weeks ago or a week ago, you and he were discussing time as a man-made feature of what we do on Earth. Can you explain the difference to me, please?
Thank you. Well, we were saying a couple of weeks ago, you're quite right, that when we measure time, we've decided on what our units of time are going to be. We call a second, and we've got a way of defining that. But that doesn't mean that you have to measure time that way, because if you'd asked somebody 2,000 years ago how long a second was, they would have looked at you blankly and said, "What are you talking about?" We have constructed the second in the more modern era. Previously, people would have talked about hours of the day, and before that they would have talked about days of the year, and before that they might have talked about seasons more. So really, there's two aspects to this. There's time in terms of the time the universe has been around, and then there's time in terms of our recording and documentation of it. We know that there's one constant in all of that, which is the speed of light. We know that light travels at 186,000 miles an hour, which is 300,000 miles a second, which is 300,000 kilometers a second. And therefore we can use that as a yardstick. And then any measurements we make, we can say we can make them relative to the speed at which light travels. And that's where this concept of a light year comes from. Light travelling for 1 year at the speed at which light travels across space is 1 light year. And that's not going to vary. And it doesn't matter where in the universe you make that measurement, you'll get the same answer. So there is a way, therefore, of dating or aging the universe, even though we have invented our way of recording time. Because light speed is a constant, we know we're talking the same language regardless of where and when in the universe we make that measurement.
Question here on the WhatsApp line. Let's go to a quick voice note. Johannes, let's have a listen.
Good morning, Lisa. This is John here. I've got a question for the Naked Scientist. I would like to hear his opinion on whether he thinks that with a combined effect of the JWST plus the new upgraded Large Hadron Collider, whether he thinks that we are standing on the cusp of a new Copernican revolution. And what would that mean, a Copernican revolution in today's terms?
Appreciate that, Chris.
What we mean by a Copernican revolution is Copernicus was the guy who wrote the book De Revolutionibus, which was all about the idea that rather than a Earth-centric universe where the entire heavens go round the Earth, what Copernicus realised over his lifetime but couldn't say because he would have been taken as a heretic and probably put to death, was that actually that's not true. And the sun is at the centre of our solar system, and our sun goes around the centre of our galaxy where there's a huge black hole, and our galaxy goes around in a big merry-go-round of other galaxies. And this is all going on all over the universe. And that was a real about shift in thinking that the Earth was not the centre of the universe. And that was brave people like Copernicus, who on his deathbed said, "This is what I think." Galileo got into trouble for saying much the same thing based on real observation. So in other words, what John is saying is, are we on the cusp of changing our way of thinking, our view of the universe and physics based on the work that's going on with tools like the James Webb Space Telescope and the Large Hadron Collider? Well, I think we're not going to suddenly see an about turn in physics, because we are doing science in a way these days, because of the way science is done, where we slowly push back the frontiers. We get more and more sure about answers, but we rarely say we've suddenly solved something. A good example of this, the Higgs boson. It's 10 years this year since the Higgs boson, sometimes called the God particle, was discovered by the Large Hadron Collider at CERN. They didn't wake up one day, turn on the particle accelerator and then say, there you go, look, we've spotted the Higgs boson. What they did over a long sequence of experiments was become more and more sure that the theory that Peter Higgs, after whom the Higgs boson is named, had advanced was the right one. And they eventually had a point where they'd got to the point where statistically they could argue they were extremely confident in the existence of this particular aspect of physics. And I think this is the way we're going to see it go. The current Large Hadron Collider experiments, they're going to start at higher and higher energies, trying to explore a range of different questions, including things like what dark matter is. One of the biggest problems in the universe. We know that when I look out into space, I can see only a fraction of the stuff that is adding gravity to the universe. Probably only a fifth of it. I can see about 5% of what must be gravitationally active in the universe. So where's the other 25%? We don't know. We call it dark matter. We don't know what it is. And therefore we have to come up with some kind of way of discovering it, because it does earmark a very important step change in physics when we get there. It will be a huge step when we find out what dark matter is, but we're not going to do it all in one go. We're going to do it by combining a range of different tools and discoveries and informing theoretical physics with experimentation and vice versa. And that will take us that next step. But I don't think we're going to see a revolution overnight like this. In the same way that the Higgs boson moved our understanding forward and made us feel more sure about how things worked, but it didn't change the way the world worked overnight. In the same way that I think probably Copernicus and Galileo changed the way we thought about the universe and gave people confidence to say those things. But they still sat on them for a lifetime, remember? They didn't just suddenly discover that one day. It was all about everyone agreeing that they were right.
Barris will be our last caller this morning. Good morning, Barris. Hope you're well.
Morning, Mr. Thank you. Chris, I'm curious to know, as you know, 567 broadcasts on an AM signal. Now, why is it that when you go into power lines or a building, the signal gets horribly distorted and nothing happens on an FM frequency? And does AM have any advantage over FM?
The difference between the two is in the frequency, and AM are waves at a much longer wavelength than FM. And the way in which the information is encoded in AM is quite different to the way the information is encoded in FM. So in order to send the speech through AM radio, what you do is you have the radio waves all at the same wavelength, so they're the same distance apart, but you add the signal of the voice to how tall the waves are, so that the waves get taller and shorter to add the speech to them. FM, frequency modulation, you have a wavelength which you're tuned to, and then you vary the frequency a little bit either side of that to add the information about the speech. So when you go near a power line, if the power line is producing some kind of radiation, then what it's going to do is add to distortion to the height of the waves of your AM radio, so that the information is lost, because suddenly that's no more meaningful information about how high the waves are, because they're being drenched out by the sounds coming off the power lines. Whereas with FM, this is not going to happen, because you've still got those important wobbles away from the core frequency, the frequency that the radio is broadcasting at either side of it. And that's not going to change, because the power lines are not producing radiation at that frequency, which can interfere with that particular broadcast.
It ties in nicely with a regular listener of our show, Chris Tudi, who's for days and days been complaining about our signal at her home. But this morning she came back just as a courtesy, because she regularly sends us a message saying the signal is bad. And she says, just to update you regarding the interference on our radio, it was caused by a new security power pack that we had installed. Thank you very much. After our IT department checked up on whether she can hear us properly. And that's connected to what you're saying now about interference when it comes to particularly AM waves.
And there's a satisfied listener for you.
Well, there's a satisfied listener. Tudi, I hope you are satisfied. Thank you so much. Dr. Chris Smith, chat to you again next Friday.
On capetalk.co.za,
on the app,
on DSTV channel 885,
and across the city on 567 AM.
Join the conversation.
This is Cape Talk.